Hi, folks. Thanks for joining in. Hope you are doing great and staying safe. This is our 40th Silicon Valley IIM meetup, and today we are going to talk about a very interesting as well as a very timely topic about eBPF. We have Harish and Mike from Levo to take us through the eBPF fundamentals, use cases, and the eBPF versus Envoy pros and cons, and finally how eBPF is being used at Levo. Harish is a co-founder at Levo, and Mike is a founding engineer. What do you, Harish and Mike?
Thank you so much, Prabhupada. Really appreciate you having us at this meetup. Wonderful to be talking about this. Levo is a security company focused on IAM observability and IAM validation. And we're going to talk about how eBPF will supercharge IAM observability. So IAM is very complex in microservices. And you guys are all IAM people, so you should completely understand what I'm talking about here. You have in microservices and APIs, you have users, you have roles, and you have numerous roles in many companies. Then you have like JSON objects that are being accessed via APIs. And what ultimately is IAM is about authorization and authentication, right? Where you need to understand, which users under what roles are accessing what API objects and APIs. And so this is a very, very complex problem in distributed systems and multiple APIs. And having runtime observability to this is very, very important. And without runtime observability, preventing IAM abuse becomes very, very hard. Having a strong security posture, making sure your IAM actually is working, requires observability into the IAM behavior. And this is why IAM observability is important. Let's actually look at some practical use cases why IAM, if you don't have IAM observability, what's going to happen? So here you have a use case of horizontal authorization abuse, where Troy is a legitimate user who's authenticated. And this actually happened at Uber very recently, where Troy accesses his receipts API for his rides from yesterday. Then he also realizes as long as he's authenticated, if he can access other people's APIs using numbers like 101, 102, 103, he was able to access Kathy's receipts and Scott's receipts. And these receipts have personally identifiable information, sensitive information, and Troy is able to access this in an unauthorized manner. And this is what we call as horizontal authorization abuse. And HackerOne recently wrote up an article saying the rise, they call this insecure direct object reference, and they call it the rise of the IDOR. So horizontal authorization abuse in APIs is a very, very common thing. And without observability, you won't be able to detect these types of behaviors. The second type of abuse that's very common is called vertical authorization abuse. Here you have a user, Joe, who belongs to the manager role of this fictitious company called Acme. And he's able to access a couple of objects called total revenue objects and customer revenue objects. This is via GraphQL. And then Jan and Tim belong to the employee role, and they're able to access only the customer revenue object. So what is vertical authorization abuse? If Jan and Tim were able to access the total revenue object, even though they're not supposed to, that is a failure in IAM or authorization, and that's what we call as privilege escalation or vertical authorization abuse. So current observability methods, without observability, we just talked about why observability is important with IAM. And current observability methods for IAM are way too intrusive. I'm going to explain the different methods and the different problems with them. But ultimately, our end goal is to understand which users under what roles are accessing what APIs and what objects. So just to give a very concrete example, when I go to my Facebook API and I look at my profile API, when I touch that, I'm potentially manipulating my profile photo, my address preferences object, my email preferences or notification preferences object. All these are objects within the API, and I need to understand how users are manipulating those things. And in order to get that observability, the common practice is to use what's known as network packet capture, and this has been around since the late 70s or early 80s. And you just basically capture packets at the network level, and you reconstruct API traffic, and then you figure out who's accessing what from that API traffic. But the issue with network packet capture is it has no TLS visibility. Especially with Diffie-Hellman keys, decrypting encrypted traffic is very, very hard problem. The other aspect is it's very CPU intensive. For modern microservices, we have hundreds and hundreds of APIs and microservices. It gets very, very hard in terms of CPU. The second common approach is using something known as reverse proxy sidecars. And this is a pattern that was established by Envoy proxy and is also being used by service mesh technologies. And what the sidecar does is, it is a full reverse proxy sitting in front of your application. And all traffic, all layer 7 traffic, HTTP traffic or API traffic is routed through that stuff. And the issue with this is it requires application changes. So if you're using Kubernetes or any sort of application, you need to configure the application so that all the traffic is routed to this reverse proxy. It also causes increased latency. And then when you have to debug something, you can't just directly debug your application. You have to also debug the sidecar container because that sidecar proxy, because that could be causing a lot of problems. Now, the third method is what we call in-app instrumentation. And in-app instrumentation was popularized by companies like New Relic and AppDynamics and Dynatrace, where they run an SDK or agent as part of your process, of your application process. And that application makes a copy of the incoming data, incoming and outgoing data. That's how they're able to look at the API traffic. And again, the issues with this type of architecture is it requires app changes because you have to include an agent as part of your application, or you have to include SDKs, has increased latency, and potentially, if the SDK has defects, your application could also crash. So, summary of the slide is current observability methods require too much change and are too intrusive in terms of cost benefit. So that's where Levo is using a newer technology that's been around for the last 6 years called eBPF, or Extended Berkeley Packet Filter. And what we do is on the left-hand side is the customer premises. We have a sensor. We have no agent. There's no code changes required, no application changes required. We have a daemon set installation where we use a eBPF sensor to transparently capture all the raw HTTP calls over which API traffic is happening. And then we extract metadata from that and send it to our SaaS to provide the observability, IAM observability I was talking about. So that's how we are using eBPF to supercharge IAM observability. I am going to now hand it over to my colleague, Mike, who's an expert in eBPF, and he's going to walk you through eBPF primer and also give you a demo. Mike, please.
Harish, there's one question. If you go back to the previous slide. So there, the question is the eBPF sensor, do you have it like per node or per pod?
Great question. I can speak to that. That is per node.
Sure, thanks.
And the daemon, the daemons that we've got for the alpha right now is basically scheduling one sensor pod, one privileged sensor pod per node.
Sure, thanks.
Okay.
So Mike, over to you. Any other questions, Prabhat?
That's what we have so far. Thanks.
Okay. And Prabhat and Harish, can you guys see my screen?
Yes, I can.
Excellent. Okay. I'll take it from there. All right, so let's start by talking about what eBPF is. eBPF stands for Extended or Enhanced BSD Packet Filter or Enhanced Berkeley Packet Filter. It is a minimal overhead method for manipulating network traffic or instrumenting kernel or user space code. It evolved from the packet filtering implementation first introduced in Linux kernel version 2.4, hence the name. Let's talk about the major components. So first we have a virtual machine that runs BPF specific bytecode in the kernel. Next, we have kernel-based helper functions that can be called from eBPF programs. And this is where most of the interesting things in eBPF happen. It's really important to note here that let's see. Next, we have callback like entry, getting ahead of myself. Next, we have kernel-based safeguards to prevent eBPF programs from hanging or crashing the kernel. This is also known as the BPF verifier. It's really important to note here that the verifier imposes severe restrictions on the size and complexity of the BPF programs we can write. This is a plus when it comes to performance, but sometimes it means we have to get creative about how we are instrumenting our code. Next, we have callback-like entry points for eBPF programs to interact with packets, sockets, system calls, kernel functions, and user space functions. Data and metadata from those instrumentation targets can be accessed with BPF helper functions. We should note here that this is an area of very active development for the kernel. New helpers are being added in each release, and we need to think very carefully about what kernel versions we want to support and what helpers are available to us in those kernels. Next, we have kernel-based map and array-like data structures for sharing data between eBPF programs and user space. And finally, we have the BPF system call. This handles a lot of functionality, including loading and attaching BPF programs and also interacting with BPF maps. All right, so let's look now at how we use eBPF to trace HTTP via the Linux socket API. This is essentially what's happening in our demo app. And it's a stripped down, what's also happening in our sensor stripped to its essentials. So our requests come in via the receive from system call. We have a receive from entry handler, and this picks up arguments that were passed to receive from, and it saves them to a BPF map. Next, we have on the other side of receive from, once the receive from system call has done all its work, the kernel will fire off another eBPF program that we've attached. And this will check the return value from receive from and see if it actually got any data. If it did, it will grab what it needs from the eBPF map. This was from pointers and such that were saved by the enter receive from trace point, and it will forward the received data to our user space sensor program. Tracing the response works pretty much the same way. So it starts with the send to system call. We have a send to entry handler that is, again, grabbing pointers to the data being transmitted. It's saving those to maps. It is then we're once send to has done its job, we're checking the return value, and assuming data was actually sent, we're using the return value and pointers stored in the maps to forward our data back to our sensor.
Mike, one question.
Yes.
In this diagram, what is running in the user space and which components are in the kernel space?
So in this diagram, the trace points and eBPF programs are running in the kernel space. The receive from and send to system calls essentially straddle user space and kernel space.
Sure. So okay, so basically server represents most of the kernel space.
Server represents the entire node or pod or what have you.
Okay.
So this is more about looking at the different modules that are touched in sequence. It doesn't, unfortunately, it doesn't do as good of a job at separating separating concerns as the previous diagram did.
Sure, thanks.
So, all right. So let's demonstrate this in action. For a demonstration, we have a Python-based API server that we built on top of a server stub we created with the Open API Generator tool. We also have a stripped down version of the eBPF-based sensor we are currently developing. The sensor provides handlers for the socket API calls used by our demo server, and it prints the captured data to standard output. I want to highlight here that we did not have to modify the server stub or the Python runtime at all to capture this data. All right, so left window is where we are going to launch our entire demo stack. So, so this starts by bringing up a virtual environment for our Python demo server and launching that. Next, we are like building our, and it's actually already up. Okay. And so if you watch the left, you will see requests and responses printed on the standard output. And in the right window, we're going to curl it. So that's pretty much it. We're sitting on send to receive from and getting everything that comes goes via the those socket API calls and returning it to Userspace. Are there any questions? Do we have any questions while we're here?
Yeah, so one thing Harish mentioned, like with eBPF, like when you compare that with proxy, you can get access to the encrypted traffic. So
right.
how does that work?
Yeah. That's a great question. Where you would essentially attach a BPF programs to different entry points, and the specific entry points that we'd be talking about are what are called uprobes, and these are entry and exit handlers for user space functions. So what we'd end up doing here is sitting on popular TLS APIs and instrumenting their send and receive data functions, and and basically following pretty much the same pattern as we do for send to and receive from, where we capture data buffers and return values and forward the same data to our sensor.
So this runs on top of like before the traffic reaches the TCP IP layer, is it?
Yes. That's the entry point we'd be targeting.
Yeah, and you said that so there are like multiple probe points, right? So for the user space function, did you mean that that we can attach a BPF program for a given system call or a set of system calls? Like how do we, like, what's the entry point or what's the trigger for a eBPF function?
You definitely we actually have several triggers or several entry points for eBPF programs, and you actually mentioned one of them in your question, which is entries and exits to system calls. So there is a and the Linux kernel provides entry and exit trace points where BPF programs can be attached for pretty much every system call in the kernel. Then you can there are actually other entry points called kprobes, where you can target any function within the kernel. So if you want to troubleshoot something at really low level or get data out of the kernel that isn't directly available via a system call's arguments, that is an option, and we've actually had to go that route to collect some metadata about the HTTP traffic that we're tracing. And then if you go up a level, there's the same idea for pretty much any user space program written in C or C++. You can find the offset for the function within that program, and then attach what are called uprobes to the entry and exit events for that function, and get the same functionality, where you can grab arguments on the way in and return values on the way out.
Sure. Then there's a request to make the text larger.
Okay, 1 second.
There's another question from Rohit. How does it work with multiple pods on a server and pods listening on different ports?
Great questions. So let me.
Maybe
I can speak to that.
Maybe showing the screen, your screen about the architecture, that would be helpful when answering that question. So.
Yes, definitely. Once I will back up to that slide in just 1 second. All right, so there's our. I just want to give the people who asked for bigger bigger text a quick moment to see this demo. And just for grins, we'll fire this off one more time. Okay, and one more time after that. So we can see the full traces coming through the sensor again. Okay, and let's bounce back to that slide. So this is probably the best the best slide to use for answering the question about handling traffic on different ports and across multiple instrumented applications, because it it points out a very different way of thinking about programming than say what a typical like Java web developer or full stack web developer is used to. If you attach a BPF program to a system call, it will run every time the system call gets called, no matter what port's involved, no matter what program is calling it. So one of the things that's in our demo application, and one of the things that anybody who's developing with eBPF and instrumenting anything needs to think about, is how to make sure that they are collecting data from the right target, and not not getting what they're interested in is getting lost in the noise from every other thing, every other call to their instrumentation target. And this is where BPF maps come in. So, and I will mention that the demo code that we just ran will be made public on GitHub right after we're done here, so people can see this for themselves. And so let's talk about BPF maps. So because a lot of different applications are running receive from, and we don't see them. Even on my machine, a lot of different applications are calling receive from, and we're not getting spammed by them in terminal window. We're only seeing request and responses on port 8080. And what you can do is stick filtering criteria into a BPF map, and then have your entry handler consult the context in which it was called, and compare that to filtering criteria within BPF maps. And it only, if it doesn't see anything it actually cares, basically, if it's not being called from a context that it cares about, it'll just return immediately. It only does interesting things if the BPF map contains the context that actually called it. And if I didn't explain that clearly enough, please tell us in the chat, and I'll see how I can clarify.
Sure. So so another question related to that, like so now so the eBPF program will be running on the node. So when you have multiple pods running on the same node, so if we go with the proxy approach, we can selectively attach a proxy for a given pod, right? But in this case, it's the same eBPF program. We don't have a control. So if we want to run the eBPF program selectively for certain pods, how do we do that? Do we define a filtering criteria in the eBPF program itself, or how to do that?
So yes, you have to. That is left to the programmer, and that's actually functionality we've had to implement. So the way we're doing that is basically a lightweight version of a firewall program.
Mike, I think what we're doing is we're allowing people to specify Kubernetes context, like namespaces or deployment names or service names, and even port numbers or even IP addresses, like what Mike was saying. We have firewall-like rules, but uses rich Kubernetes metadata. So you can say deployment equal to foo. That's the only deployment I want traffic from. So we won't care about anything else. Right. And the receive from will only be triggered for those types of pods. All other pods will be ignored.
Right. And thank you for leveling up, Harish. That's absolutely correct. In our demo application, we are filtering on process ID. just to sort of relate it to what people are actually going to be able to see on GitHub. But Harish is absolutely correct that what we're working toward right now is filtering across Kubernetes deployments and across basically source and address hosts and ports. And this is all functionality that leverages BPF Maps and has to be explicitly programmed into your BPF event handler code. Like I said, if you attach a BPF program to a particular, say, system call trace point event, it will fire every time. It's just that it only does anything interesting when the context matches criteria that you have in your maps. So it's really powerful and it's really flexible, but there's a lot that a BPF developer has to do for herself or himself.
Yeah, so basically, like the filter and logic needs to be built into the eBPF program itself, right?
Yes, it is. That's exactly correct. And the main moving part that enables that are the BPF maps.
There's another question from Rohit. Does eBPF allow dynamic update of the BPF maps to add or remove filtering criteria dynamically?
Yes, that's something that happens via the BPF system call, and there is a that can be done as many times as the user needs, and there's basic example code of that in our demo, because we have to stick a process ID into the map to enable the our BPF program, or to point our BPF programs in the right direction toward the server we want to instrument.
Yeah, another question. So I believe the eBPF program is running within its own like sandboxed environment.
Yes.
If that is the case, what are the restrictions? Can it do a network call like within the eBPF program itself?
So not with the not with the entry points that we're using. There are other eBPF program types that have different helpers available to them, that can manipulate socket buffers and such, and send data over the wire. But again, I think this is probably a good time to mention some of the detailed restrictions in the eBPF verifier, and why it's unlikely that we're going to see programs doing that in the field, even in the future. The BPF verifier limits program complexity in the latest kernel to 1 million instructions. That's like all if-else branches, all iterations of a loop. It when it does a static analysis on programs as they go in, and it it has an instruction counter that it gets incremented for each BPF bytecode instruction that it processes as it's sort of trying to follow every fork in the road. Once that counter hits 1 million in newer kernels, or 4096 in older kernels, if your program hasn't returned, or hasn't thrown in a return statement or finished up, the kernel will reject the program. The other thing to note in practical terms is that yes, there are BPF helper functions that can alter return values, but they're mainly meant for kernel developers to do troubleshooting and and testing of kernel code. They're not really meant for production use. So the
like in our case where we collect data using eBPF probes, but the actual transmission of data happens from our Userspace program, right? Maybe you want to sort of elaborate a little bit on that.
Fair enough. Yes. So once we collect data, it gets shipped across to via another subsystem in the Linux kernel called the Linux perf subsystem. And this is this is a facility for sort of shipping arbitrary blobs of data from the kernel to user space and from BPF to user space. So that's we have basically a small C struct in at the head of those blobs we're shipping to user space that provides context information for the data we've captured from our BPF programs, but all of the correlation of those contexts and reassembly of those various buffers happens on the user space side and is transmitted to the next stages in our data processing pipeline from userland.
Yeah, so with respect to the Levo implementation, I think Harish showed this eBPF sensor.
Yes.
What does it really mean? Does it include user space code plus the eBPF program?
Yes, it does.
Okay, so that's the user space program is the one which will read the data from the eBPF program, which collects the stats, and user space program is the one which will publish the data to the cloud. Is it?
Yep, exactly.
Another question. Yeah, so you mentioned about BPF Maps.
Yes.
So now in your previous diagram, we can see that it's been like multiple programs can like retrieve or write to the same map.
Correct.
Is there any control? Like, how do we control, like say define who can access a map?
There is no access control. And this is another
Mike, I think access control may not be authorization. It's more like is a file handle type of access, right?
Fair enough. Yeah. So the there in the simplest case, which is what we're using, maps that were so all of our BPF maps and all of our BPF handlers were loaded from the same object in the file system, the same compiled object. And though everything in that object can, whether it's a program, so maps and BPF programs that were created together and packaged in the same object can all see each other. I've played around a little bit with creating multiple objects and having them access each other's maps. That did not work out of the box. I know that there are ways to do it in eBPF, and the concept that I needed to research more on, and anybody else who's interested can research more on, is what's called pinning. So you can set the lifetime of BPF programs and maps to outlive their user space function, and to pick up pinned maps or pinned programs, or work with pinned maps or pinned programs that were added by other processes that may have gone away. So that's how that's how BPF programs that from different processes could potentially communicate via the same maps. That's functionality that's advanced beyond what I've played with so far.
Sure. So in this diagram, you're showing the BPF system call. Is it being used to deploy the BPF program into the kernel space?
Yes.
Then how how would the user space program communicate with the eBPF program?
Good question. So the one of the things that's set up via the BPF system call is what's called a perf buffer. And so this is a basically a collection of ring buffers that that BPF can write to, or that our BPF programs can write to, and that user space can read from. And so when we have data to ship, we call a let's see, I want to refresh my memory on it. Man, BP. Hang on. to just the size of this window. Okay. Here you go. So basically, our BPF programs are calling BPF perf event output, and in order to send a blob of data to Userspace, the Userspace is then calling epoll wait on a file descriptor related to that same perf buffer, and then processing the data that comes back to it when the kernel actually fires off an event. So,
Sure.
So it's basically event-driven polling with a timeout on the user space.
Sure. There's a question from Kesara. How does the eBPF program scale with higher throughputs?
Scale to higher throughputs? Is that what? Is that the question?
With higher throughputs. Like the scalability of the eBPF programs. More load, how would that be handled? Like?
Fair enough. So that is that requires very careful architecture on the user space side mainly. In terms of having good filtering criteria in your maps, because we don't necessarily want every byte or bit going in and out of the machine. And then also you end up with this is actually why we are writing our user space code in C++, so that we have fine-grained control over the data, the creation of buffers in user space, how they get reused, and we're trying to cut copies and memory allocations to a minimum. We're also making heavy use of multi-threading and thread safe data structures. So one thing I will plug in terms of thread safe data structures is Intel threaded build Intel's one API thread building blocks, and then or also boost fiber, and this is a way to get multiple cores involved, but to minimize the number of low-level threads and the overhead with creating them and destroying them.
So one other point around this is, like, from a scalability, if you see most architectures today, Java stack, very threaded architectures, and you're pretty much limited. Your amount of data that you can move is limited by the amount of threads and thread swapping, thrashing type of things. And we're 100% event-driven architecture. So we only use one or two threads, but pretty much event processing is the efficiency we get from events.
Right. We've taken a lot of inspiration from Nginx in that regard.
Sure. There's a question from Rohit. I think probably you answered this question before too. Regarding your demo program, if this call was an HTTPS call in the demo program, then would the BPF sensor need access to the TLS keys?
Yes. In fact, this is if there were a TLS call, we would probably only collect statistics instead of raw data from our socket API calls. And then we'd actually collect the raw data from via uprobes from the read and write functions within the TLS API. OpenSSL is actually our first target there.
Yeah, but do we need to have access to TLS keys? Because I thought
to TLS keys, we do not.
Yeah. We don't need.
Do not need access to TLS keys. If you sit on the functions that accept plain text input or return plain text output, you do not need any kind of access to TLS keys. I didn't understand that part in the first when you first asked it, but thank you for clarifying.
Sure. And there's another question: how would the eBPF programs talk to each other?
How do they talk to each other?
Yeah.
Okay, that goes back to BPF Maps. Basically, a program, the lifetime of a program is anywhere from 4,096 to to a million instructions, and they can leave things behind in maps for their colleagues to pick up.
Okay.
So the the BPF map is kind of a Dropbox or mailbox for programs to talk to each other.
So can eBPF program register some event for a given key in the BPF map? How does it know it's been updated?
So a BPF program is so that's a really good point, and that goes to some other properties of BPF programs. One of the main points of BPF, and the reason the verifier is such a stickler, is that they want BPF programs to run and return as quickly as possible. And so BPF and also BPF programs run without preemption. So the once a BPF program starts, it's going to run right through until it's done. It's not going to sit around and wait for events. So it is basically, a BPF program is the finest grain of functionality that you have.
So the trigger point is always a system call, right? Coming from the user space.
That is one of them, and that is the one we've targeted first. There are other trigger points. Like I said, there you can have trigger points on low-level kernel functions, like below the level of a system call. For instance, on send to and receive from, when we want to get when we want to grab the addresses and ports involved in, say, send to or receive from, we also have a BPF program attached to a kernel function called sock fd lookup light.
Sure. So would that mean given one eBPF program cannot directly invoke another eBPF program, but they can share data through BPF maps?
Right. So they can share data through BPF maps, but I want to clarify something about BPF programs invoking each other. There is limited functionality for BPF programs to invoke each other. One of them is the BPF to BPF call. So most of the time, on older kernels, there was no support whatsoever for functions. You had to declare everything inline. But newer programs will let you actually, do a proper BPF function call to another program you wrote, and load it in the kernel. And however, and sometimes you can pass arguments across. Most of the time, these things are leaving breadcrumbs for each other in the BPF maps. There's another older functionality that can also be very useful called a tail call, where when a BPF program has done as much as it can and it wants to hand off functionality to another BPF program, it can do so via another BPF helper called BPF tail call. And this basically invokes another full-on BPF program to pick up where it left off. You cannot pass data directly via tail call. This is also where you have to use maps. And you can only tail call, once you, from your first BPF program invocation to your last tail call, you can only tail call 32 times.
Sure. Yeah. Yeah. Maybe
juicy questions.
Yeah. We can. Thanks a lot for taking all the questions.
My pleasure.
Maybe we can go back to the demo. Do you want something else to show? Are you also planning to show so you showed us how to get this running,
mm-hmm.
And do you want to show how to publish this to the kernel as a eBPF program, and how to?
Fair enough. Okay, so that requires a bit of a dive into the source code, and I can I can drag my if we have time and want to go that route, I can drag my IDE over and start highlighting things. Is that something that people are interested in?
Maybe quickly, for example, if you can give us the steps. So I want to create a eBPF program and deploy to the kernel and invoke it. What should I be doing?
Okay, fair enough. And here, let's drag here comes the whole IDE. Okay. So should we can start with Prabhupada, please feel free to interrupt me and ask me to sort of dive into a different dive into a different file if if I'm not answering the question right. But this is main.c. This is our user space program right here. And I want to sort of call out some of our declarations. So this is a callback function that that gets triggered whenever whenever there's new data on the perf buffer coming from our BPF events. And right now we're just doing a write to standard out from the data pointer that's passed into it and for the size that's passed into it.
This can be in any language, right? This can be C, Go, Java, or any.
Good question. Your user space program can be in any language that has a C foreign function interface.
Okay.
It's because the sanest way to interact with BPF that and the BPF system call that I've discovered so far is the lib BPF project. That's written in C.
Okay. Yeah, sure.
So basically, if you want to use a different language, you have to write a wrapper around libbpf. There is a Rust wrapper around libbpf, and there is also another company has written a Go wrapper around libbpf. Those are the most promising ones. I will note that especially the Go wrapper lags behind the latest release. It tends to lag a little bit behind the latest releases of libbpf, and the libbpf API itself is in quite a bit of flux right now. There are functions that are we actually have a bunch of to-dos in our alpha code because there are libbpf APIs that are being deprecated. Our demo program actually uses the latest APIs and turns on strict mode to sort of enforce what the libbpf developers envision as the version 1.0 API. So let's see. And actually might as well show our includes here. So the interesting stuff, this is coming out of these includes are coming out of libbpf. The rest of this is standard system level includes, and we have some other constants in the header file as well. And let's see. So we have some declarations here for program names. Also, attach order matters. What we're doing, when we do our attachment order for BPF programs, we are attaching our, so that we don't leak space in our maps. We're attaching things that clean up maps before we attach things that generate map entries. So we also have a signal handler for taking us out if we get a sig hub, somebody calls kill without with arguments, or somebody hits Control C. So, all right, let's talk about what actually happens when we launch. Processing. So this is all about processing command line arguments and doing sanity checking. This is where we configure the libbpf library. And this is where we open our compiled BPF object. These are all calls into libbpf. This here is where we are sticking out, where we're getting a handle on our monitored PIDs map and plugging our current PID into the map to basically enable send to and receive from handlers for system calls from that PID. And then let's see, we're getting a hold of the perf buffer map here. This is a specification for the ring buffer that our BPF program is sending data to. This actually is initializing the entire user space data structure for that BPF program. We're specifying a number of the number of kernel pages to assign to it here. We're pointing at the map that we got our handle on, and we're also adding a pointer to the callback function that I showed you at the head of the file.
Sure.
So every new event, it basically gets the pointers from it get passed to that callback.
Sure.
And then error handling. Okay, and then here we get to attaching BPF programs. So yeah, basically we're getting a handle on each program and calling BPF program attached to stick it into the kernel. And if that doesn't work, we go and bail out.
And can you please
yes.
show us the eBPF program too?
Yes. Do you want me to jump over to that now, or do you want to walk through the rest of the user space side first?
I think because of the time limit, we
All
got
right.
some understanding. Maybe if we can cover the other side too, like how to write
Sure.
the eBPF program. So eBPF program will always be written in C?
Yes. Okay, so there are two ways to write it. You can write it in assembly, or you can write it in C.
Okay.
Anybody who's doing a lot of doing serious work in eBPF is probably going to have to learn at least a little bit of eBPF assembly, because there are cases where the eBPF verifier and the Clang optimizer sort of end up in conflict, where the BPF verifier wants to see things like bounds checks on like read and write lengths, and will only give you credit for having those bounds checks if they're really, really close to the helper where they're getting used. Whereas the optimizer says, I don't need this extraneous bounds check. I'm going to optimize it out. So something that serious BPF programmers are going to have to learn is how to use ASM templates in GCC and Clang. These are also known as the ASM volatile statements. We don't have any in here, but we've had to use them at least one place in our alpha code. So let's see. Let's talk about BPF programs. So this here is an entire BPF program. It starts with a named section. So the SEC macro is out of the libbpf helpers. We have a section name. So this is and naming matters here. So the section name is actually what libbpf uses in order to know what type of program we're dealing with and where to attach it. So everything between the slashes, tracepoint / syscalls / sys enter receive from. Tracepoint is a program type. Syscalls is the particular tracepoint entry point. And then sys enter receive from is the actual the actual trigger that we're targeting. And then we have basically a function that returns an int and takes a pointer to a context. I realize we're short on time. Actually here, let's go to our header file. This is the actual sys enter receive from context, and I have comments in here for how I got the context. And in general, I've tried to comment the heck out of this demo program. So if we don't have time to get to some of these questions, they might be answered when people take a look on GitHub.
Sure.
And then GitHub issues are also welcome if people have problems with run.sh or if people have additional questions. So I'm going to try and add a fact.md in future revisions on that demo project.
I think we can follow the README and get this up and running, right?
Yes. There's so it's been tested against Manjaro Linux and then Debian 11 successfully, and there's a list of packages. There's a list of required packages on the README.
Sure, thanks. So there's a question from Rohit. I think you answered that. What language is best suited to write a BPF sensor?
Okay, so our BPF programs we're writing in C. The Userspace code, you can pretty much use any language where you can add a wrapper around the BPF. So as long as you can call into C from whatever whatever Userspace language you're using, you can use that. You'll want to think about performance, how much of a factor performance is when you do. If you're just collecting and compiling statistics, you can use anything. It doesn't need to be all that performant because your user space code isn't doing all that much. If you're doing something really data intensive, Rust, C, or C++ are probably your best bets, and Go might be a good middle ground.
Sure. Yeah. Maybe we can move to the next slide.
Okay. Well, so all right, so we're basically sort of at the end of the slides that I wanted to present, and if we're running out of time, I can yield the floor back to Harish. But if there are any other questions, I'm happy to answer them.
I think that's all the questions we have so far. Maybe we can move to the next section.
Okay, got it. Harish, since I'm already sharing, I will jump ahead to your next slide.
Yeah, thank you, sir. That's going to be the service mesh. I mean, we have 3 minutes. I'll make it brief. So the questions are actually go to the previous slides, sir. Mike.
Yes.
Not this one. Just the so the topic here is like, hey, eBPF versus service mesh, right? I mean, like, when should I select one or the other? Like, if you only want observability and you want to do this in a very, very efficient, no friction, no node code changes, no application changes way, eBPF is the way to go. But service mesh is not only about observability. Service mesh has all kinds of other functionality. Like, service mesh has access control policies. It has things like authorization of OPA. You can inject OPA into your sidecar and do a bunch of authorization. So service mesh offers you a whole bunch of other functionalities that if you have requirements for those things, then that's something to look at. But with service mesh comes complexity. Like almost a 10x increase in complexity of operating Kubernetes. Kubernetes itself is complex. On top of that, you add service mesh. There's like so much more complexity in terms of adding sidecar, debugging the sidecar, making sure the sidecar resource constraints are met, all these types of things. So that's why you need to step back and ask, hey, what are my goals? And if I only need observability, and what is my easiest ways to get observability? If there's also alternatives to sidecar-based service mesh. Cilium is a company, Isovalent is the commercial company, and Cilium is the open source project. Cilium has a zero sidecar eBPF-based service mesh that can offer similar functionality like Istio. Not all the functionality offered by Istio, but pretty close, I would think. And they're getting, every day they're making more progress. So that's pretty much it in terms of service mesh comparison. Any questions?
No, Harish. I think we're clear.
Yeah. Okay, great. Thank you. That wraps up our session for today.
Yeah, thank you very much, Harish and Mike. I think it's a very informative session. You took like all the questions, and I think we got a very good understanding. And probably, Mike, if you can put some links on your README file, like if someone wants to get started with eBPF, like what are the best resources to get started?
Right.
So that'd be helpful too.
Right. I will add those. I'll probably start with what I have so far, and then add those resources sections or references sections to the README as once it's up and people can start browsing. And like I said, issues are questions and problems that people have with this are welcome. We will address this as we find time. But this is definitely something want to provide to the community, you know, and it's sort of the template I wish I had when I started this, you know, back when I joined Levo.
Sure. Yeah. Thanks again, Mike and Harish. This is very informative, and thank you very much, everyone.